Hi everyone. This is the final demonstration for our neural network inference on FPGA project for the ECE 6213 class. I am Osama Yusuf speaking on behalf of myself as well as my partner Joseph Ree. In terms of the overview, so we have a web server that hosts a web camera. The processing system then can request a live image from this web server. The web server responds with an image. The processing system can then process this image to actually match the neural network's expectations because the image that has been captured by the web server actually has a much higher resolution. So we do some image processing to actually make it compatible with the neural network's expectations. Once the image has been processed, we can directly feed it to the neural network, which is sitting on the programmable logic component of the board via a DMA send channel. Once the neural network inference operation has completed, its output can actually be read back by the processing system via a DMA receive channel. So next, I'm going to demonstrate end-to-end inference on the neural network, on the board along with our web camera integration. So the first part that we will look at is the web server itself. So it's a simple web server that we have coded in Python using a very popular web server framework called Flask. So all the web server does is that it exposes an endpoint for capturing an image. So here is a snapshot of what our web server GUI looks like. So this is basically a workaround for having a direct USB camera connected to the FPGA board. So we can see it next working live. I'm first going to show the code, then I'm going to show how to start our web server, and then we'll also see how to demonstrate how to capture an image directly. So let's do that. So first, here's our code base. It's basically the only interesting thing happening here is that we have this endpoint capture image. And all it does is that it can directly send the image that's being mirrored on its camera source defined here, right? So we have a camera source that's continuously generating frames. And then this capture image endpoint, all it's doing is that it's taking a static image based on that live camera feed and then sending it to whoever the request came from. So we can then start the server. I'm going to start the server now. Okay, so the server is now up and running. A current limitation of this approach is that the server has to be hosted locally since the FPGA port needs to access it via the Ethernet connection. So I'll just copy it here, and purposes of demonstration, I'll just paste it here. Now, the endpoint that we have implemented is capture image. So this is how this would be accessed. So as soon as I press enter here, you can see that the web server has basically served my request with a downloaded image, right? And if I go to the actual URL, the live feed will actually pop up. You can see that we have the live feed here, and then this is the image I took. Apologies for the image quality. So again, the idea is that through this mechanism, what the onboard processing system can do is that whenever we have to take an image, we can simply send a request to this URL through this web server approach that I just demonstrated. And we could use that to simply get an image for performing inference directly on the board. So next, I'm going to talk about the actual inference operation on the board. Okay, so this is a live camera feed currently overlooking my FPGA board. The one thing to note here is that we have this SD card that's currently plugged into the board. And our board also allows us to set different boot configuration through these 5 switches here. So the current mode is actually set to boot up from the SD card. And on the SD card, we actually have a complete Linux operating system. And so the hard processor that's present on the board, or the PS, actually runs a full-fledged Linux operating system. Uh, it's actually referred to as a pink operating system, and I'm going to talk about that in a few moments. But the other thing to note here is that over here, we also have an Ethernet connection. And so this Ethernet port of this board is actually connected to the same network as my host system on which the web server is running. So this is very important. And then this Ethernet connection is also, like, it also allows us to directly access the Linux operating system that's running on this board uh, through a simple SSH environment. So next I'm going to show how to actually connect to our board and then how to run the end-to-end inference examples that we have created for this project. So I'll just open a quick command prompt here. And then what we can do, since we're connected to the same network as the board, we can directly ping the board. And then the board itself, the ping operating system actually assigns itself a really nice host name for us to make it easier to access it. So as you can see over here, we are getting network packets back, which means that the board is actually on the same network. So next, what we can do is that simply SSH into the board operating system. So that's precisely what I'm doing right here. It asks for a password. So here we are inside the board now. Now, this Pink operating system for our board, it also allows us to directly run Python notebooks. So there is a Jupyter server that's already running on this board, on this Pink environment. So next, what I'll do is I'll access that server. And the way we do this is just by accessing the host name, and then this is the port on which the server is running. Again, asking for a password. Yeah. So now we're currently accessing the files that are present, the Jupyter Notebook files that are present on the board. This is the end-to-end inference notebook that we've prepared. So I'm just going to open that real quick. Okay, so we're inside this notebook that we have for end-to-end inference now. Over here, we're just explaining the summary of the project, which we don't need to in this video. So the first step is the real-time image capture. So assuming we have a server that's already up and running, what we can do is that simply send a request to the same URL through the web server. And again, you see the capture image URL here. And what it's going to do is that it's going to hit the server, and then it's basically going to ask for an image. So once I actually run all of this, once I run this notebook, I'll scroll back up here. Yeah, so the first step is that we actually connect to the web server to get an image. We get a response back from the web server. And over here, I'm simply displaying that image. Again, this is a picture that I've taken in which I basically have my phone up, and then this is the testing image that we want to perform inference on. So as you can see, this image is, pretty large in resolution, and it's pretty different compared to traditional MNIST testing images, right? So if I was to just resize this into the appropriate dimensions needed for the network, our network would never be able to classify that this is actually the digit 0. So we need to perform processing on this image, and we need to localize this digit. Like, we need to create sort of like a bounding box around this, and we need to make sure that this digit is, appearing cleanly in the image. So that's the next step. We basically do some image processing here. And since I've already executed the notebook directly entirely, you can see that our image processing algorithm, what it's doing is that it firstly loads the raw image, right? We firstly convert it into a grayscale image. We then apply a thresholding parameter as well as binarization. So binarization basically means that there shouldn't be any shades of gray. The pixels can either be a 0 or a 1, right? So pixels in the image can either be completely black or completely white. Once we have this thresholded plus binarized image, we simply extract the bounding box through through this library from pill image, which is a famous, a very popular image processing library in Python. And then this is what our final image actually looks like. So the last thing we need to do is that this image is still, in terms of resolution, it's actually much bigger compared to what the network expects. So our network actually expects an input of an 18 by 18 image. As you can see, firstly, this image is not squared, and secondly, it still has a lot more pixels than needed by our network. So that's exactly what we do over here. We have a simple function that can firstly resize the image to our desired width and height, which is 18 by 18. And then for all of the remaining pixels, what it does is that it just expands the image and then basically appends zeros or black pixels around the corners to make sure that the image is squared. So now you can see after the final processing, we have a nice 18 by 18 image that has been pre-processed, cleaned, and now it fully matches our neural network's expectations. So the final step is to actually send this image to the neural network, right? So our FPGA is actually can actually be programmed through a bit stream that contains the neural network uh, dynamically, like on the fly. Our FPGA actually gets programmed as soon as we execute this particular block. And I think what we can do is I can execute this and we can see in real time how that changes. So I'll just turn on the camera feed again. So as you can see, the blue light is actually lit up here, right? So this blue light actually indicates that the FPGA, the programmable logic, has already been programmed. The reason why it's already blue is because I executed this notebook already. So if I were to um, just run this particular cell, so if I were to program the FPGA based on this cell, we can see in real time, um, we should be able to see that, yeah. So the light blinks and then the FPGA gets programmed again. Just to demonstrate this again, because I'm not sure if this is going to be apparent in the actual recording. So the blue light is actually going to blink once the FPGA bit stream has been loaded. So yeah, over here. So as soon as the overlay is loaded, the light, corresponding light on the FPGA actually blinks. So back to the notebook. So what we're doing here is that we have a separate driver that we've written, and then in essence, the idea is that the image that we have based on the final processing, xtest variable here, is actually sent to the neural network through a DMA send and receive channel. Sorry, through a DMA send channel. The output that we get from that, which is Y hardware here, we simply apply a max argument max function here, which basically tells us what's the output neuron with the highest weight value. And in the current mapping with the MNIST handwritten digit dataset, you can see that the predicted digit was actually 0 and the input image was actually 0. So all in all, what shown is that on our board, we can actually have a real-time image capture mechanism. We can do some image processing, and then finally, we can perform inference directly on the board. And then this neural network is actually sitting on the programmable logic. So all of the actual inference operation happens on the programmable logic, whereas this notebook and this Python code itself is actually being executed on the processing system. So this concludes our demo for end-to-end inference on the FPGA board with web camera integration.